Hey, so today we're going to do sort of a fun talk, and it's really about pattern classification, which is an old name for a type of machine learning. And really, it's about the most common type of machine learning we're going to do, which is a binary classification problem. So this talk, I originally gave these exact slides a long time ago. You can see the date there. And I've left it unchanged. So the language is a little bit different than you might see currently in machine learning, but I actually think it's a little bit easier to understand and motivate and see what's going on. So I really like this talk because it's just a different perspective. There's a Medium article that has all of this in words, if that's helpful, and there should be a link down below to that. So what are we talking about here? We're talking about binary classification problems. Binary meaning two outcomes for the most part. Some of these are multi-class classification, meaning more than two. But we're doing a hypothesis test. We're trying to determine if something is true in the world or not. So for example, we might look at a weld that was made, sticking two pieces of metal together, and say, hey, is that a good weld or a bad weld, right? Or for this problem, what we're going to look at is we're going to listen to a recording, and we're going to say, hey, is that a marine mammal, like a whale, or is it a cargo ship? So the way we're going to do that is we're going to listen to some data. We're going to receive the data. So this will be just a recording time series. We talked about audio data a lot recently. We're then going to extract features from that data. So we're going to summarize it in different ways, and then we're going to do some math to automatically label it. So in this case, either a whale or a ship. Like I mentioned here, this also goes under a bunch of different names. So like I mentioned, these slides have been unchanged for 12 years. So pattern classification also goes by decision theory, hypothesis testing, or machine learning. So there you go. So first, let's talk through like a speaker recognition example. So you're receiving some audio file. You pull out some formant frequencies, which is the frequencies of the tones that people are speaking in. Maybe the speaking rate, some other features, and then you sort of automatically assign it to a class. So this is a really common problem that happens, and it's really useful for things like conference calls or those kind of items. So this is something that happens in the real world real frequently, and it's that exact same process. We're just doing more than one class if there's more than two classes, right? If there's more than two speakers. Obviously, there's a bunch of other examples of classification you can do. So here is a binary classifier that talks about is a gearbox broken or not? So they're listening to the gearbox. They've got some features in blue and green. So sort of listening to the RMS, the loudness, and the kurtosis, which is another statistical measure of probability distribution. And they're looking at those two, and they're saying, hey, we can actually predict when the gearbox starts weakening before things actually fail. So a classifier here would take in those features and say, is the thing going to fail soon or not, right? So binary classifier. The example we're going to go deep into today, fairly deep, is listening to this recording and trying to decide, is it a whale or a boat, right? So a marine mammal or a cargo ship. Marine mammals sort of make a like ooh sound, right? Like whale call. And cargo ships sound more like right? So you get those two sort of very different sounds. But if you just look at a recording of it, it's not totally clear. So the plots on the right are not actually a recording. They are the magnitude of 200 different samples. So what we've done here is we've looked at the sort of loudness of the each individual sample. It's normalized in a certain way, and this is all theoretical data, right? Hypothetical, made up. But we're looking at the loudness of each individual sample and saying, hey, that recording on average was this loud. This recording on average was that loud, right? So when we plot them on top of each other, what we can see is in general the red, which is going to be our ships this whole time. Blue is whales. So our red ships are slightly louder. But they're not so much louder that it's obvious how to make a decision, right? If the two sets were totally disjoint, you could just draw a line between them and say, hey, everything that's super loud is a boat, and everything that's not is a whale. Because these overlap, that's why we get into sort of statistical decision theory, or what we now call machine learning. So probably we could draw a line somewhere in there that would let us separate these classes a little bit, right? It's going to have some errors because they overlap some, but let's explore what that might look like. So this is a histogram of the two classes. So the magnitude has switched to the x-axis, right? So that's the same scale as was previously on the y-axis, and now we've got the count, which is the number of occurrences in each bin. So we can see that the whales are indeed a little bit quieter than the marine mammals, than the ships in red. And so in general, when something's very loud, it's very likely to be a boat, and when it's very quiet, it's very likely to be a whale. And then there's some cases in the middle that are really tough to call. So one thing we could do is we could just draw a decision line that puts, says, hey, everything on the right is going to be a cargo ship, everything on the left is going to be a whale, and we pick a line at a location that sort of, we just pick one sort of arbitrarily right now that gets the bulk of the answers correct, right? One issue is histograms are very sensitive to bin location. So this is actually the same data with different bins, and you can see it's a totally different looking shape. And our decision line, the one we would have guessed, moved a lot, right? We're down, well, maybe not a huge amount, but we're down quite a bit. So we want a more formal way of thinking about this, right? Something that's not as sensitive as histograms. So what can we do? Well, one thing we can do is treat this as a probability. So if you're not familiar with conditional probability, this is gonna I'll talk through it with words. All this symbol means is the probability of a hypothesis one. Hypothesis one in this case is a marine mammal, given some data. And this is the probability of hypothesis 2 given our data. So these are actually the things we want. In our case, these two probabilities sum to 1. So every example is either a marine mammal or a ship. It's never both. It's never neither. So that's super helpful. And really, this is what we want to know. So we want to know it because if the marine mammal, the probability of a marine mammal given our data is more likely than the probability of a ship given the data, then we want to say, hey, it's probably a marine mammal, and vice versa, right? So this is just the same thing the other way, that the inequality is reversed, and then if the probability is less of the marine mammal than the ship, then we guess the ship. Right? So sometimes we write this with this inequality facing both directions, and we're going to make some assumptions here that let us stir the math around and clean things up. So what we're going to do is we're going to say, hey, we think the two hypotheses are equally likely. So 50-50. And remember from earlier, they're disjoint, so 50-50 is a sort of a reasonable first guess if you don't know anything else. And then we can actually find the probability of the data given the hypothesis. So we've gone and reversed these two, and it's the probability of the data given the hypothesis 1 is true and hypothesis 2 is true. And you'll just trust me, we can stir the math around to find that. We've reversed these, and that's super helpful because the probability of the data given a hypothesis we can estimate from the samples we have, right? We have a bunch of samples from hypothesis 1 and a bunch of samples from hypothesis 2, and so we can estimate the probability distribution somehow. One way we can estimate it is we can say, hey, we think it's a normal distribution, right? So a Gaussian distribution, those are the same thing, a bell curve, right? Different communities often call the same thing by different terms. So we say, hey, when you have a normal distribution, all you need to know is the mean and the standard deviation, and you can draw the curve. So here are the curves for the two data. So this is the same histograms or whatever that we've been showing, but I just fit a bell curve, a normal distribution, a Gaussian, to both of them. This makes drawing the threshold much more clear, right? The location that they cross when they're equally likely is our decision boundary, and it's very robust, right? You can do this all in math. There's an inequality. Everybody's happy. So what does that mean for classification accuracy? Well, here what we're looking at is everything to the left of this boundary, we're going to say is a marine mammal, a whale. So everything over here that's shaded in blue, the area under this curve, is correctly identified whales. So everything to the left of this line we say is a whale. And then everything that's under this blue curve, this probability density function, that integral of that is going to give us probability. And so the area under this curve is the sort of the total probability of marine mammal, right? Correctly identifying a marine mammal, I should say. What about this other part of the curve? Well, that's the part you get wrong. So these are specifically marine mammals that you called cargo ships. So they are incorrectly identified. Now, this goes by different names in different communities. So sometimes people will talk about probability of misdetection and probability of false alarm. Sometimes they'll talk about type 1 error and type 2 error. Sometimes they'll talk about precision and recall. But for this case, I really like being very explicit about it. This particular example is what happens when you mislabel a whale, right? Similarly, we can do the red curve. So now everything to the right of our threshold we're calling a ship. The red curve is actually ships. So now this red one is correct classification of ships. So it's reversed from before. And this is incorrect classification of ships. So this would be things that are actually a boat, but we're calling a whale. Right? We get them wrong. So you'll notice there's two different kinds of error. Well, what's interesting about that threshold then is this is actually our minimum error threshold with the assumptions we've made. So when these are equally likely probabilities, the place where they cross is the minimum error. And you can see that where if you slid this to the right a little bit, you would be adding just a little bit less correct whale and a little bit more correct subtracting a little bit more correct ship, right? Because the curves have crossed, so the area under the red curve would be bigger, and same thing the other way. So this crossing point is actually our minimum error classifier. So that's kind of cool. It's worth noting that if the hypotheses are not equally likely, we can actually just scale them up. So here we say that ships are twice as likely. So 2/3 of the cases are ships, 1/3 are whales. We can just increase the probability here, and it's still our crossing point is the minimum error classifier. And then just in passing, I want to mention that you can actually do stuff also with the costs. So if it turns out mislabeling a ship or mislabeling a whale costs different amounts, you can go through and do all the math, and you can do it with the probabilities and stuff, and you can come up with a nice closed form classifier that depends on the data, the means, the standard deviations, some threshold that comes from all these things. So that's pretty nice. So a minimum cost classifier could actually be over quite a ways. So for example, you could want to very rarely miss a whale, but you're fine calling a lot of ships whales or whatever. So you slide that boundary over. Okay. So we've picked this line as our minimum probability error. We're back in equal probability, like equal likelihood hypotheses, equal cost, all that stuff. And so we've picked this location. But when we go and look at our actual data, the error is much higher than we predicted. So we see more wrong answers than we thought we were going to see. What's going on here? Well, the underlying distributions are not Gaussian, right? I mentioned earlier this is synthetic data, but it turns out one of them is a normal curve, a Gaussian curve, the whales. The other ones were a uniform distribution, a box, right? So they have this much chunkier shape. The theory for a minimum error classifier still applies, that it's the crossing location, but here the actual crossing location is shown in black, and the crossing location for the Gaussians before was in green. So because we used the wrong distribution to summarize things, we were off a little bit. One cool thing is we weren't off a ton. Right? So because things are still sort of mound-shaped, we mostly ended up kind of okay. So it's not perfect, but it's not terrible. All right. So we're seeing a lot of errors still there, right? So why are we able to, when you listen to these sounds, you could be able to tell the difference, but we're not doing a good job classifying? And the answer is because we're using one feature. We're only talking about amplitude here. And when we listen to way more stuff than just how loud the signal is, right? So here's an example. It's the same data on the x-axis, but I've turned it into a scatter plot now, and we've also got data on the y-axis. So just to be really clear about this, here's our curves from before, and you can see that if we took this scatter plot and collapsed it down onto the x-axis, we get these two distributions that are really familiar now, right? The same things, and you can see sort of how it looks mound-shaped and all the rest. So this makes sense. On the y-axis, though, we actually see this is the true underlying distributions for both of them. So in this case, they're both normal distributions, but they have different standard deviations, different widths, right? So they're centered at the same location, but they have different widths. Interestingly, you get the same classifier where you choose the crossing lines as the optimal, but in this case you'd have two crossing lines. So anything centered we would call red, ship, and anything on the tails we would call blue, whale. One thing I want to note is that there is correlation between these signals. So this is just saying that the joint probability is not the product of the independent ones, or of the two separate ones. Our actual data in blue, or our synthetic data, shows an obvious correlation, right? It shows some structure to it. If we randomly distributed them independently in both directions, we get much more of like a symmetric cloud, right? Something that spreads out everywhere. When you see this diagonal streak, that's a linear correlation. So it's got some structure to it. To look at that in 3D, this is actually the distribution. So same magnitude frequency. Here we're looking at probability density. So how likely something is to happen, and you can see this structure to it. This is the other hypothesis, the ship, and so you see it's normally distributed one direction, and then the other direction it's got that uniform distribution, and it doesn't have that correlation, right? So we've got these two different clouds. Whoa! So in this case, we actually know the true underlying distribution of all the classes and all the features, so we can draw an optimal test. So this is called a likelihood ratio test, and this is actually our minimum error test in the same sense as the other one. So you'll notice it's not just a straight line anymore. Now it's these kind of curves. And in fact, you'll see in general, as you add more and more features, you'll just get, you go from like a point distinction to lines to planes and so on, right? And you'll get, if you know the actual distributions, you'll get some interesting curves. Now, when we look at this, we can actually find that it kind of makes sense. So areas where the red is more common, we're generally going to call a ship. So this upper triangle and this lower area. And then the big streak across the middle, it looks like blue is more common, so we're going to label it for blue. So this is a binary classifier. It's disjoint. It's got two different areas. This is our optimal test. Oh my God. What did all this have to do with machine learning, right? So the task of machine learning is, if I don't know those distributions, if I don't know the optimal place to draw those lines to get a minimum error classifier, what can I do that gives me a good approximation of these, right? So that's one way to think about machine learning, and it's kind of different than the way it's taught a lot of times now. So I just like giving that other perspective. So it's the same task. We want to label this stuff, but we want to try to come up with these lines straight from the data instead of from like knowing the underlying distributions. So one thing we could do is we could just draw a line. We could figure out what the best single line is to draw in this thing. I want to be a little careful here. This is something that has not aged especially well. So I mentioned that this might be a SVM, which is a support vector machine, or a neural network. There have been huge advances in both of those areas since I made this slide, and so and even before. But very simple SVMs and neural nets and other linear classifiers do just draw a line. Obviously, they can get much more complex and do really fancy stuff also. But this might be like the best linear classifier for this thing, and you can see it's not going to do as well, but it's kind of a sensible line, right? We can also do other things. So this is a radically different approach. So what we've done here is we've partitioned the space up, and we've made these things called Voronoi tessellations. But basically, it's just these little shapes. And what we've done in each one, let's come over here. We've said, what is the line that separates each one from its neighbor? Equidistant. So between each point, there's a line, and it's perpendicular to the line between the two points, and it's spaced in the middle. And that gives you these little convex holes, these little shapes. And what you do for the classifier in this case is you just say, hey, I'm going to pick red for all the ones that have a red point in them, and blue for all the ones that have a blue point in them. Right? So this is called a nearest neighbor classifier. And really all you're doing is for any given point in here, you just plop a point down and you say, hey, what's the closest other point? What's this one? Well, then that whole area is red, right? That's it. That's the classifier. Surprisingly, that's actually machine learning, right? It doesn't feel like it's learning. It doesn't feel like there's artificial intelligence in there. But this is actually a classifier that gets used a lot. It has some really nice properties. So one of them is that in the limit of infinite data, the error is bounded at double the ideal classifier. So that's pretty surprising. This is like not a bad first thing to do. And there's a ton of other ones. So you might have heard of decision trees. Decision trees start by saying they pick one feature at a time, typically, and they say, hey, is that feature bigger or less than a number? So that's like drawing a boundary, not at a diagonal, right, instead of a slope-intercept kind of thing. It just picks, it's always a vertical or a horizontal line. So it says, hey, the first divide I'm going to make is I'm going to say, is this more or less than some number in magnitude? Then, like a tree, on each of those branches, each of these areas, we're going to divide it again, and we're going to do it on frequency. So we're going to say, on the first branch, if it's to the left of this vertical one, then we draw this other horizontal line, and so on, and we keep sort of drawing branches, and this is our optimal decision tree in this case. Optimal meaning the one we came up with the cost function we had. And if we overlap it with our ideal boundaries, we see that we get it's sort of a reasonable approximation, right? It's starting to learn something. So decision trees are just one more method of machine learning. There are a ton, but many of them that do this supervised binary classification are really just about dividing this thing up, drawing lines in this decision space, right? That's one way to think about it. And that's really the way a lot of classification works. All right. One thing sometimes people ask is why don't you just draw the perfect line, right? Why don't you go through with every point and like grab all the blue ones and leave all the other ones? And the answer is this generally doesn't do well when you have new data. So what we're trying to do is learn from this data so that we can predict the labels of new points, right? So if we get a new recording in that has an amplitude and a frequency, we can guess whether it's a whale or a ship. We can like automatically apply that label. And if we draw some really complicated curve, in general, we do worse than if we draw a simpler curve. Cool. So there are a bunch of implementation issues. So things can be computationally really complex. High dimensional data can be hard. You have to have labeled stuff. So you'll notice that I started with some data with labels on it, meaning that it had categories that were automatically labeled. And so we had to go through and start with that. If you don't have labeled data, you're in a space called unsupervised learning, and it's much less successful or straightforward. You also have to choose your features. So this is something that is less commonly talked about in a lot of data science because we start with clean data sets or whatever. But figuring out what features to use is really a big question. I think this was a bigger question 12 years ago. I think now we're often throwing everything in and letting the classifier figure it out because the computers have gotten better. So this was really my conclusions for when I was talking to academic folks and basically saying the jargon and math should scare you off, and there's a lot of really cool stuff you can do. Obviously, you know that you're studying data science. So the last thing I'll say is I pulled a lot of this from this book, Pattern Classification, the second edition, and the book is actually really good. I think it gives this kind of perspective. And in the appendices, it has the best overview, like a couple of pages of linear algebra and probability applied to these problems that I've ever seen. So I really recommend checking this one out. It's very different than the current way people talk about machine learning. It's more like this. But I think it's helpful to get a totally different perspective and a bunch of proofs and all that. So thanks.